In the previous chapter, we looked at the vapor power system, where the working fluid was water vapor. Now, instead of using just water vapor, you could use any other gas. So in this chapter, we are going to look at a general gas power system. Our main focus would be on the two systems. One is called the internal combustion engine and one is the gas turbine power system. And we are going to replace water vapor by air. So we are going to look at air standard analysis of internal combustion engine and the air standard analysis of gas power turbine system. In the internal combustion engine, we're going to look at two cycles. One is called the Otto cycle and the other is called the diesel cycle. And the names are probably familiar to you now. We are going to look at PV diagram, TS diagram, property evaluation as we have been doing, look at the energy and entropy balances, and then the overall thermal efficiency. For the air standard gas turbine power system, we are going to look at the Brayton cycle and again follow the same type of analysis. There are other cycles as well, like Ericsson cycle, Stirling cycle, which are available in the book, but I'm not going to discuss them in this lecture. So internal combustion engine, which is called ICE, it's used in all the modern automobiles, trains, buses, and they work on two different principles. One is called spark ignition engine and the other one is called compression ignition engine. And the difference is that in the spark ignition engine, once you feed the fuel mixture, which contains fuel and air, then we provide a spark, basically ignite it by using a spark plug. And that's normally used in automobiles or cars, which use low power requirements, so which is less than 300 horsepower. The compression ignition engine is used for higher efficiencies and higher performances, higher power requirements, and which are used in trucks, buses, trains, and so on. And they basically require you to compress the air at a much higher pressure, and then once you compress the air to a much higher pressure and temperature, and then when you inject fuel into it, it spontaneously ignites. So there is no spark involved there. Just by the mixture of the air, highly compressed air at a high temperature, along with the fuel, automatically creates combustion. So here is a general design of an reciprocating internal combustion engine. This is the kind of engine that you have in your cars that we drive. And it has various parts. You have a bore, which is the diameter here of this cylinder. So we have a cylinder here, and this is a piston which goes up and down. And of course, these are the two valves, which one is intake valve, one is outlet valve, and then you have this spark plug. So let's look at the various terms which are listed here. So the bore, which is right there, is basically the internal diameter of the cylinder in which the piston moves up and down. A stroke is a distance that piston moves in one direction. So it may be in the beginning right at the top, and then it might go all the way down to the bottom here, or it may be starting at the bottom here and can go all the way to the top. So that would be the distance it traveled in one stroke in one direction is called the stroke. The clearance volume is the minimum cylinder volume. So when this piston is right at the top here, then there is a small volume which is still left in the cylinder, and that's called the clearance volume. So it will be just above this line, above this horizontal line, just this volume right there. And that's called the position of the piston at that point is called the top dead center. So the position of the piston when the cylinder volume is minimum. Similarly, we have the bottom dead center. That would be the lowest position of the piston, which would be somewhere right there. The displacement volume is, of course, how much volume the piston sweeps in one stroke. So that will be the volume of the cylinder going from here all the way to the top there. The compression ratio R would be the volume at the top dead center divided by volume at the bottom dead center. So the volume of the piston volume of the cylinder when the piston is right at the bottom here, so that will be this entire volume, divided by the volume of this top clearance or clearance volume, which would be when the piston is right at the top, which would be right there. So the volume would be only this much. So you can see that this ratio is always going to be more than 1. And of course, there's then crankshaft, which is this piece here, which converts the piston motion to the rotary motion. So there are 4 basic strokes in this internal combustion engine, reciprocating internal combustion engine. We have intake stroke, which means initially the piston is right at the top and then it moves down. That's when the air or the fuel mixture would get into this cylinder. Then we have a compression stroke, when the piston moves back up and compresses the fuel mixture. The power stroke, when there is ignition taking place here. So during the power stroke, the explosion would take place, or the combustion would take place, and the piston would move down. And during the exhaust stroke, then the piston moves up again and pushes out the exhaust gases from the other wall. And so that's what is shown here. Intake stroke is when initially the piston is here and then it moves out. So the pressure doesn't really change here, but only the volume increases, and that's what this is. And the intake closes here, and then we have the compression. So now you have this valve, which was intake valve, closes, so gases cannot leave. And now you start compressing, so volume decreases, pressure increases. So during the power stroke is the stroke during which the power is basically generated or utilized, because once explosion takes place, as a force of this explosion, this piston would be pushed back, and as a result the crankshaft would be moving, which will then generate the motion of the vehicle. And then the final would be the exhaust stroke right here, when the exhaust gases are expelled. So during this whole process, you can see the pressure changes continuously. So just to get an idea of how much work we are going to get out of this, there is something called mean effective pressure, and that's defined as the net work for one cycle divided by the displacement volume. So you remember that in general the definition of the pressure is integral of P dV. So if the pressure is constant, then it will be just change in volume. So change in volume would be the volume when the piston is at the bottom dead center and to the piston when is the top dead center. So this difference in volume is the displacement volume. And so this mean effective pressure basically gives us an average pressure for this entire cycle. And higher the mean effective pressure, MEP, greater the net work be produced for the same speed. So as I said, we can in general have any gas, but just for the reason for simplicity, we are going to use air as our gas. So this is called air standard analysis, where working fluid is air as an ideal gas. We are going to assume that the combustion process is replaced by a heat transfer from an external source. So we don't need to worry about basically combustion process, which itself is much more complicated. And we can just say, okay, the heat has been, certain amount of heat has been supplied there. No intake or exhaust process. Heat transfer occurs at the constant volume. So what we are saying is that instead of saying air is taken in and then after it burns is thrown out, which will create it to be a controlled volume system, because now we have mass coming in and mass going out. To again simplify it, we are going to just assume that the same air gets circulated, so it becomes a closed system rather than an open system. And then we are assuming that all processes are internally reversible, so again, which would make our life a little easier. We can also do what is known as cold air standard analysis, where even the heat capacities are considered to be constant. And you know that properties of the ideal gases are given in this table. So let's look at air standard Otto cycle. So this is basically consists of two types of processes. Two of them are constant volume process and two of them are isentropic process. So you start from 1 to 2, which is this compression process where this is an isentropic process. That means the entropy remains constant. Then 2 to 3 is where the heat is absorbed. In reality, it would be the combustion, but since we are replacing combustion by just heat transfer process, this is where the heat would be taken in from some external source, and that's a constant volume process. Then 3 to 4 is the power stroke, where that heat is transferred to move this vehicle, let's say. And then the 4 to 1 would be the exhaust process, where basically in our case it would be the heat is being rejected. So we have two constant volume process and two isentropic process, which is a very idealized system. And this is how we are going to draw that on a PV diagram. So constant volume process would be vertical lines, and then these are the isentropic process. And if you do a TS diagram, then the isentropic process would be vertical lines, 1, 2, and then 3, 4, and the constant volume process would be these other lines. So you should know how to draw these air standard Otto cycle or other cycles that we are going to look here on a PV or a TS diagram. So to analyze this Otto cycle, let's look at the processes individually. So remember, process 2, 3 and 4, 1, these are constant volume process right here. So that means the work done during those two processes would be 0. And similarly 1, 2 and 3 and 4, 1, 2 is this one and 3, 4 this one, which are isentropic process. That means isentropic for an ideal gas would also mean adiabatic, so there is no heat transfer. So therefore Q1, 2 and Q3, 4 would be 0. And now we have a closed system. As we said, we are assuming the same air is circulating, so it's a closed system. And we can easily assume there is no change in kinetic energy and potential energy. Then using the first law of thermodynamics, which says delta U is Q minus W, we can write down, let's say for 1, 2, during process 1 to 2, since it's an isentropic process, Q is 0, and therefore the work done per unit mass would be just change in internal energy. Similarly, work done per unit mass for process 3 to 4 would be equal to change in internal energy. And for the other two processes, when the volume is constant, there is no work done. So in that case, the heat transfer per unit mass would be again change in internal energy. So basically, whether it's work done or heat transfer, they all would be just difference of change in internal energy. And so that's very easy to do because we have tables to read out the internal energy values for air. And so the net work done would be W34 minus W12 over M. Remember, W34 is the power stroke when the work gets output, and 1 to 2 is when you do the compression. That means you are doing work on the system, so that would be negative. And so the net work done would be the difference of these two, which is given by that. And therefore the efficiency would be W cycle divided by Q23, Q23 being the amount of energy that has been supplied by the external source during this process, 23. And so if you now substitute W cycle and then Q23 from here, we get the efficiency, which is 1 minus U4 minus U1 divided by U3 minus U2. So this gives us a very simple relationship between change in internal energies and the efficiency of the cycle.